Hey, Tim DeStasio here, and it is another episode of Psychrometric Saturday. We have still a lot to learn about sensible heat ratio. Of course, that is when we divide our sensible load divided by our total heat load. So let's take, for example, our sensible load in our load calculation was 24,000. Our total load was 30,000. That, of course, just leaves 6,000 for latent heat. That gives us a 0.80 sensible heat ratio. Now, we have to draw a line through our psychrometric chart. One point on that line hits our 0.80 on our sensible heat ratio scale because that's what our load gave us. The line also must intersect our desired indoor conditions, usually 75 degrees dry bulb, 55 degree of dew point. So that's that dot right there. Our line connects those two dots. It goes all the way through the chart. And we have to make supply air that is in this quadrant of the chart. Not here, not there, not there, but in this quadrant. Now, in reality, our air is going to be somewhere around the saturation line because when we cool our air, we cool it, we take sensible heat away from it until we hit the saturation curve, and then we slide down the curve. And so our air ends up being really close to our saturation curve. Now, a little bit of air bypasses the cooling coil, either gets around it or the air goes through the fins, and for the most part, just a little bit of air remains unaffected. And so in reality, our supply air conditions very rarely is right here exactly on the saturation curve. No, usually we have to backtrack a little bit, and it ends up being around the 90 to 95% relative humidity curve. That's usually where our supply air ends. Now, as long as we are in this quadrant, and we're usually just barely in that quadrant, but as long as we're below this line, then we should be able to maintain our conditions. Now, what happens when we replace some older equipment that maybe was less efficient, maybe didn't move as much airflow, with newer, higher efficiency equipment with a better blower motor? Is it guaranteed that we're going to be able to maintain conditions? Well, let me give you an example. So let's say that we have a 30,000 total heat load, 24,000 of that is sensible. We have a 0.80 sensible heat ratio. And our old piece of equipment did this. It had a 25 degree temperature drop across it. And when we plug this into our CFM formula, CFMs equals BTU sensible divided by, and we have to multiply 1.1 times our temperature drop together first, we come up with this formula right here. Our temperature coils, we had a good 25 degree temperature drop, and maybe we had an old PSC motor, and maybe our ductwork wasn't great. So instead of it being a 30,000 or 2.5 ton AC unit that was moving 1,000 CFMs, it was only moving 872 CFMs. But notice what happens when that old unit was running, and it did a great job. We had 872 CFMs, and we had a 25 degree temperature drop. So we were cooling our air all the way from our starting point, which is our return air conditions, 75 degree dry bulb, 55 degree dew point. We were cooling it around 20 degree drop. We hit our saturation curve, and then we went down the curve all the way until we hit 50 degrees. That gave us a 25 degree temperature drop. And yes, a little bit of air did bypass, so our air conditions, our supply air conditions were right around right there, and it maintained conditions, and it did a great job. Maybe it wasn't as energy efficient, but then you go as a contractor and you sell them a new 2.5 ton or 30,000 BTU air conditioning unit, and it's a lot higher SEER, and now it has an ECM motor, so we're going to be able to definitely move that 1,000 CFM that we wanted to move before. But are we going to be able to maintain the same conditions? Well, you would think, I've got a newer efficiency unit, I should be able to take care of it. But here's the problem. Newer, higher efficiency units don't have as high of a temperature drop. So this number is a lot lower. A lot of times it's only around 20 degrees. And the reason is that it takes a lot of energy to bring our air conditions all the way down here to saturation curve and to keep cooling it down all the way down here. Instead, higher efficiency units just get you part of the way. So let's see what happens now when we install that brand new higher efficiency unit. Instead of having a 25 degree drop across the coil. We only had a 20-degree drop across the coil. What's going to be our required CFMs? So when we do the math here, 24,000 divided by, and in parentheses, 1.1, that's a constant, times only a 20-degree temperature drop, we come up with 1,090 CFMs. Well, that ECM motor, if we tell it to do 1,090 CFMs on a 2.5-ton unit, we probably can make it do that. So again, it doesn't look like we're going to have a problem, but notice what happens with only that 20-degree temperature drop. We are still cooling the air. We're cooling the air, and then when we hit 20 degrees, we barely make it to the saturation curve, and then we stop cooling. And so have we removed the moisture to dehumidify that air? No, we have not. Which quadrant are we in? We are not in this quadrant anymore. We are here in this quadrant. So we may be able to satisfy the temperature of the room, but all of a sudden we cannot satisfy the humidity. And now that brand new higher efficiency unit that we installed cannot maintain the humidity. We have a very angry customer at us. So how do we avoid this? We got to do ACCA manual S, which means that we match the sensible and the latent capabilities of the system that we're putting in at the design conditions that we're putting them in to make sure that they can satisfy not only the sensible load, but also the latent load. And we're going to be talking a lot about ACCA Manual S in another week or so when I hold an ACCA Manual S simplified class. So stay tuned for that. And as always, thanks for watching Psychrometric Saturday.